So now we will be diving into the basic characteristics of soils. As the name implies, it sounds fundamentals and it is the necessary contents for these modules. So I will be dealing with the origin of soils. It is a long story, but in short, soils are mainly formed by weathering process. Quite simple. Then we may want to classify our soils as a fine and coarse materials. This is the first classifications to better understand our soils because understanding the properties and the engineering behavior of soil is crucial. So these aspects are entirely dependent on soil's particle size. So we are going to deal with the grain size distributions and in particular focus on fine grain soils because it would be very sensitive to water, while the coarse grain soils are meant to be what the parent rock has. Very expected, but clay materials a bit different. Why? Are you curious about this? Why? Stay tuned. I will later on explain about this. And then in most cases, the soils deform when subjected to certain loads. It is necessary to discuss about plasticity, described by Atterberg limit tests on fine grain soils. Only for fine grain soils, clay and sands. Then we will classify our soil in details according to particle size and plasticities with some specific rules. Let's go to the origin of soils. In most cases, soil originated from weathering process, which consists of physical and chemicals. Rocks become soil particles with the same mineralogical compositions as the parent rock has. At the same time, or separately, rock also become soil particles due to chemical process, like action of water, oxygen, and carbon dioxide. So their characteristics can differ from the parent rock. Mechanical things just become small particles, and their characteristics and then engineering behavior quite similar from the parent rocks. But after chemical process and chemical weathering process, their major characteristic already changed. So what is important is that both the physical, mechanical weathering and the chemical weathering process can occur in situ, not in the lab, in situ out there. So our soil is comprised of mixture of coarse and fine grained soils. You can see bigger particles, even also organic matters, and even very fine materials. Their engineering behavior affected by these particles. For examples, coarse grain is the majority. So this soil's engineering behavior is followed by coarse grains behaviors. And then this soil's majority is fine materials. These engineering behaviors followed by the fine grain soils behaviors. That's why we need to differentiate it. How much portions bigger particle has. in the soils. The origin and formation of the soils will affect the soil's mineralogy and depends on parent rock characteristics and also particle size distributions. And then that specific particle shapes is very sharp or rounded, something like that, and soil structures. It is the looks like fluctuated or something very randomly allocated. So certainly these factors control the engineering behavior of soils, strength, stiffness, mechanical behavior, and then permeability and volume change, hydraulic behaviors. So as mentioned earlier, in most cases, our soils exist in the form of mixtures. So depending on the particle size, soils may be described and classified. For the fine-grained soils, their plasticities is governing factors in the engineering behavior. And for the coarse-grained soils, their strength and interlocking is crucial. It is not that the plasticity is the ability of soil to deform without any cracking, any breaking. So I brought some bite-sized video for your better understand. Let's
Our topic for today is soil formation. Soil is formed by the combination of physical, chemical, and biological processes in which huge rocks are broken down into smaller particles over a long period of time. Rocks undergo a process of expansion and contraction in which they expand during the day and contract during the night due to the constant rise and fall in temperature. However, not all parts of a rock undergo expansion and contraction at the same rate, resulting in the formation of cracks. Gradually, these cracks cause the rocks to break down into smaller pieces. With time, these smaller pieces convert into particles and form soil. Water plays an important role in soil formation. Water that gets collected in the cracks of rocks sometimes freezes, which helps in widening the cracks. Also, flowing river water helps in the wearing down of rocks over time, which results in the formation of soil. Strong blowing winds also rub against rocks and help in wearing them down. Lastly, some living organisms like lichens that grow on rock surfaces release certain substances that cause rock surfaces to powder down and form a thin layer of soil.
It looks funny. Yeah. Now our soils exist in the form of mixtures coming from chemical and mechanical weathering process. That's why our particles vary. Let's see. Technically, the size ranges from over 100 mm to less than 0.001 mm. Each particle has different shapes and mineralogy, which has a significant impact on soils engineering behaviors. Again, engineering behavior is mechanical behavior, how heavy it resists the loads, and hydraulic behavior, how fast the water flows through the soil particles. So some sort of the ASTM stands for American Society for Testing and Materials. And British standards set particle size to differentiate gravels, sand, silt, and clay. This is the international standards. Who set this? American and British. Singapore also have our own local guide. So this ASTM BS have a little bit different particle size that are associated with sieve opening size. Yes, it's because every single soil is different with the soil where they are located. That's why British set their own soil for their nationals, and then US set their own particle size for USA. Singapore only for Singapore. That's why different nations set different particle size. These sieve analyses give us fine and coarse grain soils. See, normally sand and gravels are classified into coarse grain soils, which is greater than 0.075 mm, the particle size. And clay and silt considered as fine-grained soils less than 0.075 mm. This is the fundamental classifications, coarse grain and fine grain. When it comes to the coarse grain soils, it is angular with different shapes and different angularity, different surface characteristics. As you can see here, they have the same minerals as parent rocks. So as a geotech engineers, you coarse grain soil is relatively easy to deal with, and then very easy to figure out their characteristics. Just think through the parent rock characteristics. So it means that we can easily infer the characteristics from the parent rocks. Thank you. On the other hand, fine-grained soils, totally different story. It is normally called clay minerals. The main group of crystalline materials that makes up clay are kaolinites, aelites, montts, molybdenites. Speak up. Follow me. Kaolinites, illites, montmolybdenites. These kaolinite, illites, montmolybdenites characterize clay soils because, as you can see, they have different structures, different chemical compositions, very, very small things in different structures as compared to these simple coarse grain materials. Okay, guys, everyone, let's focus. Most of the clay minerals we are interested in are composed of oxygen and silicons, which are the most abundant elements on Earth, which is silicate. These silicates are a group of mineral with structural units called silica tetrahedron. A central silica cation, which is the positively charged ion, is surrounded by 4 oxygen anions, negatively charged ions, one at each corner of the tetrahedrons, which is the silicates, silica tetrahedrons. These silica tetrahedron combine to form sit, which is called silicate sit. Very thin layer of these silica tetrahedrons. Silicates, one of the unit to form clay. Similarly, alumina sit or gibbsite sit, which is formed by the combination of alumina octahedrons, which consists of aluminum ion surrounded by 6 oxygen and hydroxyl atoms in the octahedrons, which is the gibbsites. These two seeds, silica seed, gibbsite seed, combine on their way and exhibit kaolinites, illites, montmolybdenites. I'm going to show you different combination of silica seed, gibbsite seed. These 3 important clay materials, kaolinites, illites, montmolybdenites, consist of repeating layer of silica seed and gibbsite seed. Depending on how it looks like, their engineering behavior is different. This kaolinite has the structures that consist of 1 silica seed and 1 alumina seed bonded together into a layer and stacked repeatedly. These layers are bonded together with hydrogen bonds very tightly. This kaolinite is common in clay in tropical regions. So Singapore marine clay are also kaolinite. In light, it consists of repeated layer of 1 alumina gibbsite seed and sandwiched by 2 silica seeds. So these layers are bonded together with potassium ion. And what about the montmolybdenites? It has a structure similar to that of illites, but the layers are held together by van der Waals forces. This layer bonded by van der Waals forces and exchangeable ions. So a large amount of water is attached into the space between the layers. These van der Waals force attracts water. That's why most of the clay take the clay, take the clay dough, take the mud, and then just leave at the room temperatures. They cannot dry it out easily, right? This is the clay layer characteristics. What about the sand? You can take the sand and gravels and suck in the water and take it out and just leave these room temperatures out there probably 10 minutes after 10 minutes or are dried out. Clay cannot due to this kind of clay layer structures. These structures attract water. So these clay minerals has their own characteristics affected by these mineral structures. 5 characteristics. It is strongly influenced by the presence of water. Water is always source to occur to create some problematic situations, very deformable. Make our clay layer deformable. Water. So these minerals attract water, and the water on the mineral surface is not easily removed. How do we remove? Put it on the oven. More than 100 Celsius. And 24 hours to 48 hours, even 7 days. Yeah, we need still 7 days. Our clay now totally dried up. So these water-related properties atomic limits. Have you heard about atomic limits? What about this? Kim Yong-min limits. Mr. Andrew Chang limits. Atomic is the name of the person, professors. Mr. Atomic proposed some testing method to identify our clay's plasticity behaviors. So in week 6, you're supposed to do this. And our clay minerals have a large specific surface and active surface so that the clay particles are surrounded by waters. Waters attracted on the large surface. And the individual clay particles interact through their observed water clay. And then due to the complex interaction between clay particles, we have different types of clay structures. Perhaps these structures governs clay engineering behaviors. Okay, hi Prof. Now we roughly understand the major soil groups, say fine grain soil and coarse grain soil. Coarse grain soil quite similar to the engineering behavior of mother rock, parent rocks. In fine grain soils, or it is clay, we have 3 different types of clay, kaolinite, illite, monzonite. They has a very specific behavior according to water, right? And then, how can we classify it? Yeah, of course, this is certainly done by particle size. based on the specific number 0.075 according to ASTM, right? What next? Is it done? No. We have a specific two types of additional tests to refine our soil classifications. This is the laboratory tests. I mean, conducted this test in lab. One is the sieve analysis, one is the hydrometer analysis. The sieve analysis is for coarse grain soils, and the hydrometer analysis is for fine grain soils. The distribution of particle size can be obtained by screening the soil with the known weight of the soil through the stack of sieve for coarse grain soils. We put our soil mixtures, totally dried one, and then shake it, and then our soils falls on individual sieve, and then each sieve has a different openings. And then at the end, last pan, we have fine grain soils. We take these soils and then goes to the hydrometer analysis. At first, for the coarse grain soil, we conduct sieve analysis. Yes, sieve analysis is the fundamentals. It means that we will get grain size distribution of coarse soil from the sieve analysis. We prepare dry soils that will be passed through a series of standard sieve having progressively smaller mesh size. Then we determine soil mass of the soils retained at each sieve. Then calculate the cumulative percentage by passing each sieve. This is the sieve numbers and the corresponding sieve opening size. This is typical US standard ASTM. And then the soil passing through number 200 sieve. Here, 0.075. This is the criteria, threshold, differentiate our coarse and fine grain soils. Passing through 200 sieve or soil retained on pan is called fine grain soils. So when you collect the fine grain soil from the sieve analysis at the last pan, then we can conduct hydrometer analysis. Here is the sieve analysis procedures. We weigh mass retained on each sieve and then get the summation of total mass and then calculated cumulative and then find the soil passing each sieve and then calculate the percentage. That's all. Percent finer or percent passing is the percentage of particle by weight smaller than a particular sieve size. This is the typical Excel sheet for the calculations. This column is the sieve size. This is the soil mass retained in each sieve. This mass one is now 0. This one is 40 grams, something like that. Then we can calculate cumulative mass. Of course, we can summation of the here to here and then continuously addition the retained soil mass. Then we can get percent final according to the final total mass of the soil, dry soils. After this number of percent finals, we will get this curve. Percent of finals. And then around here, we will have 0.075. It means that we have done a sieve analysis for coarse-grained soils because based on this curve, we will produce some parameters to characterize the coarse-grained soils. Later on, I will explain how to read this grain size distribution curve. So, okay, we have coarse grain, fine grains. And in order to differentiate these two things, we conducted sieve analysis. From the sieve analysis, we will get this curve. Probably all materials, these are, here is the 0.075. These materials are all coarse grain soil. So, hi prof, where is the fine grain soils? Fine grain soils. It looks like flat. Is something wrong? We haven't conducted hydrometer tests yet. We take the final, for example, assume this sieve is the number 200. The opening size is 0.075. It means that this soil passing 200 sieve numbers, it means that these soils, fine grain soils. This fine grain soil graphically represented this straight line. So we need make this line more details using hydrometer tests to continue to grain size distribution of fine fractions. This method can determine grain size of fine materials using sedimentation theory. Wow, what is the sedimentation theory, prof? Simple. Large particles in suspension in a liquid settle more quickly than small particles. Yeah, it is true, right? Makes sense. Very common things. It is assumed that all particles have a similar density and shapes because all the fine material passing through the sieve number 200, they all are quite similar. And then their density and shape is all are same. So we take a small quantity of dry powder. I'm saying powder because it is because quite fine materials. So we take a small quantity of dry fine grain soils, rough approximately 50 grams, and then thoroughly mix it with water to form kind of pastes. And then this paste is placed in a 1 liter glass cylinders. And then water should be add up to 1 liter max. And then shake. And then hydrometers, you see this is the hydrometers, can be placed in the glass cylinders. And then Using your stopwatch, we record hydrometer height and time. Using these equations, we determine diameter of particles. D is the fine-grained particle size, and then mu is the water viscosity, Z is the hydrometer height, and then GS is specific gravity, rho W is the water density, and then G is the gravity. Because this theory is based on sedimentation, larger particles settle quickly by gravity. And then TD is time. Then we can complete fine materials grain size distributions. Initially, it was flat. Now, so as of the sieve number 200, 0.075 mm, right-hand side, coarse grain soils, their grain size distribution done by sieve analysis. After this sieve analysis, we will get a lump sum of certain amount of fine grain soils. This one, take this, put it on hydrometer test, we will get grain size distribution of fine grain soils. Y-axis is the percent finer and x-axis is the grain size in terms of on a semi-log scale. Sieve analysis.
Welcome to the CTTP training videos. ASHTO T27, Sieve Analysis of Fine and Coarse Aggregates.
Ashito is from
Obtain
USA.
a representative field sample of aggregate. Dry the sample to a constant mass at 230 plus or minus 9 degrees Fahrenheit. After drying, cool the sample to room temperature.
We should have dry samples.
Then record the dry weight. Ensure that the sample size meets specification requirements. Stack the sieves in order with those having the largest openings on top. Transfer the sample to the sieve stack without loss of aggregate. Hand sieve the sample or use a mechanical shaker set to the calibrated time. After sieving, remove each sieve from the stack. Remove trapped aggregate from undersized openings. Empty each sieve and record the weight of material retained. During this process, check for overloaded sieves. Note that individual or cumulative weights may be recorded, and the method chosen will affect subsequent calculations.
We await the retained soils for each sieve. Then we can process the soil of weights via our Excel spreadsheet.
Use a soft paintbrush to clean finer sieves. This will prevent damage to the more delicate screens. Finally, record the weight of material in the pan.
This is fine grain, right? In the pan.
Calculate the percent retained and percent passing each sieve. Report the percent passing each sieve to the nearest 1% except the number 200 sieve. For this sieve, report to the nearest 0.1% for values less than 10 and to the nearest 1% for values greater than or equal to 10.
I will also brought some bite-sized video for hydrometer for fine grain soils.
Today we are going to demonstrate the hydrometer analysis to determine the particle size distribution of fine-grained soil in accordance with ASTM D7982. Hydrometer analysis is applicable only for the soil particles passing number 200C. This video will cover the process of hydrometer analysis test for a given soil sample. If the particle size of the soil sample is less than 0.075 millimeters, we need to conduct the hydrometer analysis in order to determine the grain size distribution. Take 50 grams of soil sample passing number 200C. Place it in a cup and add 125 milliliters of the dispersing agent. In this experiment, we will use a 40 gram per liter sodium hexametaphosphate solution. Agitate the mixture until the soil is thoroughly wet. Let the soil soak for at least 10 minutes. While the soil is soaking, add 125 milliliters of the dispersing agent into the control cylinder and fill it with distilled water to the mark. Shake the cylinder in such a way that the contents are mixed thoroughly. Take the reading at the top of the meniscus formed by the hydrometer stem and the control solution. This reading is called the zero correction. Also take the reading of the top and bottom meniscus reading. The difference between the two is called the meniscus correction. Keep the hydrometer in the control solution. When needed, we will take out the hydrometer from there. After taking the reading, we will place the hydrometer back into the control cylinder. Transfer the soil slurry into a mixer by adding more distilled water. Mix the solution for a period of 2 minutes. Immediately transfer the soil slurry into the empty sedimentation cylinder. Add distilled water up to the mark. Cover the open end of the cylinder with the stopper and secure it with the palm of your hand. Then turn the cylinder upside down and back upright for a period of 1 minute. The cylinder should be inverted once in 2 seconds. Set the cylinder down and start recording the time. Remove the stopper from the cylinder. Insert the hydrometer very slowly. Take the first reading and record the time. The reading should be taken by observing the top of the meniscus. After taking the reading, the hydrometer needs to be removed slowly and placed back into the control cylinder. Take hydrometer readings after elapsed time of 2, 4, 8, 15, 30, 60, and 120 minutes, and then again at 24 hours. The following formula are used for the data analysis. Percent finer and particle diameter can be determined from the hydrometer readings. For the calculation, we need to have some standard charts and tables. Specific gravity of water at different temperatures can be obtained from this table. This table shows the viscosity of water at different temperatures.
So we have full set of grain size distributions, gravel, sand, and fines from the sieve analysis, from the hydrometer test. What kind of informations can we pick up from the curve? Basically, we can analyze the particle size from the curve. In this curve, near 78% of soil pass the sieve that represent gravels, right? It means that only 20% of soil retained at this sieve. 20% cannot pass through the same size sieve. So it means that gravel is only 20%, not the majority of the soil. What about sand? Only less than 2% of the soil pass the sieve number 200. And then approximately 78% of the soil retains above sieve number 200. As a result, it represents sand. So these soils, the majority is sand. And then we are able to obtain another curve fitting parameters that represents the shape of this curve. From the sieve analysis, grain size distribution curve, we can take the portion of gravel, the portion of sand, the portion of fine, and then curve fitting parameters. We have 3 values describing soil particle size. First one is the D10. D10 denote the size of soil particles such that 10% of the particles are smaller than that size. Similarly, D30, D6, 60 all are same. So what you're gonna do is just read off the value of x-axis. So D10 is here. So you can read off the size of the soils. D30, D60. Hi, Pro, why D50? Why not D70? Soil mechanics is entirely empirical. Before proposing D10, D30, D60, our pioneer should have considered D20, D40, D70, something like that. And then three of them is quite standard, and then the parameters that clearly show our soil's grain size distribution. That's why only 10, D30, D60. So based on these 3 values, we can define 2 curve fitting parameters. One is the uniformity coefficients and the coefficient of curvatures. We are going to use these 2 coefficients to determine whether the soil is well graded or poorly graded. Let's say we have a CJ and CU within these ranges. We can call it this soil is well graded. Well graded gravel, well graded sand. And then these 2 values falls on out of these ranges. It's a poorly graded sand, poorly graded gravels. Let's calculate CU/CZ using these grain size distributions. CU is the D60 over D10. D60 is here, and then following this line and meet up this our grain size distribution curve and read off the size. And D10 here and read off here 0.15, and then CU is a 2.0. CZ is 0.64. Is it within these ranges? No. So this soil is poorly graded. We have a variety of shapes, right? But I can tell you that we have three representative curves to explain general understanding of the grain size distributions. One is the flatter, one is the steeper. The flatter one is the larger range of particle size from here to here. And steeper one is the smaller size of ranges, just here to here, right? So the platter curve soil type C is called well graded, well distributed from fine to gravels. It means that there's no excess particles in any size ranges. What about this steeper? Soil A is so-called uniform, not the poorly graded. It has the high proportion of particle size within these narrow limits. But it is poorly graded. But it is also uniform soils. What about this fluctuated curve? Soil B, it is gap graded soils. It means that particles of both ranges, both the large and small size are present, but it has relatively low proportion of particles of intermediate size. After these soil classification, as grain size distributions, I will focus on fine grain soils. Fine grain soil to investigate the plasticity behaviors and atomic limits. Okay, let's take a 10-minute break. Then let's continue to where we left off.